Good evening, everyone. Welcome to the ninth week of online discussion on topic water and wastewater treatment. The course is being taken by Professor Bhanu Prakash Belanki from IIT Turkey, and my name is Minettam Prakash, and I am from IIT Kanpur. I am here as a uh, part of my TA duty as a PMRF fellowship. So welcome to the week 9. So as usual, this online discussion happen on every Tuesday, and the timing is fixed. And we meet with the help of this Google Meet link. And the recording of this session is being uploaded on this YouTube channel. You can access this YouTube channel. This Google link has been already shared with you. This is being shared with you on. This is this is being shared with you every week, so you can go miss if you have any kind of doubt, you can go back and join watch the recording of the previous session that has happened in the last weekend prior to that. So in this week we will be discussing this in week 9. These 9 topics were sorry, these 5 topics were discussed. That is filtration, then depth filtration, the design of sand filter. Good evening, Saket Gupta. Then design of sand filter and surface filtration, the disinfection and hardness. So in this, so when I was going through the topic, the most of the questions are related to this filtration and deep filtration only. And actually, most of there are 9 questions, and all of them are being related to this filtration only. The hardness topic, I have covered some question which I have already discussed in maybe in big 2 or big 3. So I will be recapping those things. About disinfection, this has been discussed in big 7. So I think in big 7, yeah, big 6, I don't remember thoroughly. So either it was in big 6 only, so you can go and check the recording session of big 6, where we have talked where there was a discussion of there was a problem solving based on only disinfection. There were 9 or 10 question, and after that some concept related to disinfection and design of sand. Yes, we will be discussing about this design of sand filter. So as usual, every week in this week also we will be discussing some important question which is being expected from you to solve during your assignment or quiz, and some concept which I will be discussing at the end of lectures. So in between the discussion, if you have any kind of doubt, you can directly write in the chat box, or you can raise your hand. And if you think I am going too fast or too slow, you can just object. You can just stop me, and you can ask me to repeat the things which I have discussed. I will be happy to do that. So with that, I will be moving forward. The first question is related to depth filtration. So what are the following, which of the following are the mechanism of depth filtration? That is, these 4 options are there. So before discussing, so my pattern is that before discussing a particular question, I will be first discussing its fundamentals. So before knowing discussing about the term depth filtration, simply one should know what is simple filtration and then what is depth filtration. Okay. So with that, first I will discuss about the filtration. So everyone is aware of the filtration. So you can think it as a last step of your water treatment, whether it is wastewater treatment or whether it is generally in wastewater treatment filtration is done, but it's rare. It's some when the purpose is what the purpose of treating wastewater, then filtration depend. But suppose if I have to dispose my wastewater, then it is generally filtration does not happen. But for drinking water, means if you have collected water from river or groundwater and you have treated it, then before passing it to the community or before passing to any kind of society, you have to make sure that that water is filtered. So filtration is everything. Everyone know the definition of filtration, that I have to reduce the turbidity of the water. Means turbidity of the water, means in at the end of the session I will be discussing some of the mechanism. Like everyone know that if you have gone through the lectures, you must be aware of the thing that is there is one rapid sand filtration, slow sand filtration. So I won't be going on that. I will be just scratching on the surface, and I will we will be just looking at the definition of filtration, depth filtration, and depending upon that question, depending upon the our requirement of the question, I will be try. We will be trying. Yeah, I will be trying to answer that question. Okay. So if we look at the filtration, in filtration particles are captured primarily on the surface of the filter medium. So what happened that if you have miss whenever a person listen to the term filtration, what happened that this is our filter media. Generally, what the people imagine that there will be a media, water containing some suspended solid, or some suspended solid will be coming. The filter water will pass through it, and the particle matter which has size more than this pore size of this filter media will get trapped on the surface, and this will be a simple filtration. This is the most common and most genuine definition. If you have everyone is familiar with the filtration, but but what happened that in real system, what we do not encounter this thing. We have a much more bigger mechanism behind this filtration. We have something called media. So what are those media will I will be discussing in detail in the next slide. But for now, just remember that we are just talking about this filtration. So in filtration, the particles are captured primarily on the surface of the filter medium. Remember, this is combination of many media. Miss we will be seeing in what are those medium and all these things. But when general in general meaning of the filtration is happen that all the suspended solid which is there will be trapped here, and the filtered water will pass through that medium. Okay, it typically involves the retention of particles that are larger than the pore size of the filter meter. So remember, it will have some pore size. So if you are a kind of researcher, if you have gone through the environmental lab, you must have used filter for filtering some of your samples. So there is some filter syringe and all these things. Generally those are cylindrical in sorry yes, circular in nature, and it has a pore size of 0.42 0.42 micrometer. Okay, na 10 ki power minus 6 meter. Okay, so generally this is the range of below this all the samples are dissolved samples. Okay, dissolved solids. So what happened that in I'm talking about in our laboratory. Okay, na, so if you have gone through your laboratory, you must have used a circular filter media. uh, and what happened that when we filter our sample which we collect from anywhere, then what happened that all the dissolved solid which is there will pass through the filter media, and the suspended solid will get trapped on the will get trapped on the surface of filter medium. Okay, so this happen also in wastewater treatment also. Means if you have tank, water passing through it, only there will this combination will have some kind of pore size. Only those particles will retain whose pore size is larger than the pore size of this medium. Okay, filter efficiency can be influenced by factors such as pore size, flow rate, and pressure. uh, I think this is very common. Miss what kind of particle I have to remove all depend upon the pore size of this medium. Okay, common type include surface filtration methods such as membrane filtration and cartridge filtration. Okay, I hope you cartridge filtration means it's kind of some cartridge that you have listen, and membrane means some which I was saying. This is a kind of membrane filter. Means there is a membrane, water is passing, and we sometimes what happen that we always apply pressure and all this thing. But in wastewater treatment, we do not apply any external pressure. All things work by gravity. Okay, so these are. On the other hand, depth filtration involves the capture of the particle within the depth of the filter medium. Okay, so now imagine what happens that there is this thing, and there is some kind of media here. It contains some kind of sand, gravel, blah blah blah. Okay, so what will happen that water will go there, and instead of getting trapped here, what will happen that it will pass through this media, and it will get trapped between the pore size of those gravel or those sand. So what is happening that it is not getting trapped on the surface of media, it is getting trapped on this depth. So that's why it is known as depth filtration. So remember what happened, that in wastewater we do not use the term depth filtration, we use the term filtration only, but that means depth filtration, because we don't want to use the term this depth continuously everywhere. So whatever book, whatever, if you are going through some study material, so if they are mentioning about filtration, they are just mentioning about depth filtration. Okay, so everywhere in water treatment, everywhere the treatment is happening by this depth. What happened, that water will pass through this media. So instead of writing depth filtration, they are writing simple filtration. But if you look in the deep, both are two separate thing. Okay, so just don't get confused what I have discussed there. Whatever is written there, they are using some conventional method, that yes, if a medium is there that contains some kind of sand and all this thing, sand and all the thing, then that water, then that will be termed as depth filtration. Okay, the particle penetrate deeper in the filter medium where they are trapped toward the material depths. Mechanism of capture include interception, sieving, sedimentation, diffusion, and absorption within the filter media. Okay, so remember here the mechanism was pore size, flow rate, not mechanism, influenced by pore size, flow rate, and pressure. But in this case, but in this case, what is happening, that they are talking about these four mechanism. It offer higher filtration efficiency and longer service compared to the surface filtration. You can imagine also, miss, for filtering some x amount of water, x liter of water, if you are using just a membrane, and at another hand you are using some kind of filter system, so obviously this filter system will be more efficient and comparable, means more efficient and long lasting thing. Okay, so in summary, both filtration and depth filtration involve the separation of particles from fluid. Depth filtration operates by trapping particle within the depth of the filter medium, whereas filtration typically capture the particle on the surface of the medium. Okay, I hope this is clear. So I will be discussing more about the mechanism of capture involved in the include actually remember, I have written only three because these are main mechanism. Okay, now interception, sieving, and absorption. But apart from that, sedimentation, diffusion, and absorption are also prevalent methods in filtration method. Okay, so in interception, what happen? Interception particle are captured as they come in the contact with the filter media fibers or pores. When the particle move through the filter medium, they may collide and may trapped by the fibers and pores. This mechanism is particularly effective for particles that are larger than the pore size of the medium. So what happens is generally, this is your filter media. So it will your grains, yeah, your whatever the media is there will be arranged in this manner. So it will be leaving some kind of pores. So what water containing suspended solid will come here, and if the particle, if the particle size is larger than it will get trapped here. Okay, and the water, filtered water, will get down here. So that is what is written here. When the particle moves through the filter medium, they may collide and become trapped by the fibers or pores. So they are getting trapped by these pores. Okay, and this will only happen when the particle size are larger than the pore size of the filter media. Okay, I hope this is clear to you. Next is something called sieving. Sieving occurs when the particles are retained by the small pores within the filter media. As fluid passes through the filter media, the particles that are larger than the pore size become trapped with the pores, while the smaller particles of the fluid can pass through more easily. This mechanism is based on the size execution principle and is effective for wide range of particle size. So again, they are talking about this pore size only. Okay, coming to this absorption involves the addition of particles to the surface of filtration media due to attractive force such as electrostatic force. Okay, So I hope everyone is aware of this term adsorption. I won't be discussing it here. It's simple interaction between contaminant, means general solids present in the water and the one media, so generally solid media only. Okay, so adsorption. Adsorption involves the addition of particles to the surface of filter due to attractive force such as electrostatic force, van der Waals force, or chemical interaction. Particle may adhere to the surface of filter media as they pass through it, leading to the removal from the. Again, same thing will happen here. What will happen that suppose this is your media and this is your, sorry, this is your particle size, this is your particle size. So what will happen that it will have some adsorption capacity, so water containing suspended solid will come here and the particle which is present here will get attached to this solid here. Okay, so what will happen that in this way the water coming from here will be free from any kind of suspended solid. Okay, so remember it's not like that this mechanism only this mechanism is happening. Yeah, only this mechanism, all mechanism are happening all together at some place depending upon the what kind of pore size, what kind of media is present in the system also, and what kind of suspended solid present are present in the system. So last option is sedimentation. In some cases particle may settle out of suspension and accumulate on the surface of the filter media. Okay, enhancing the filtration process. Okay, so sedimentation, all of you know this thing. So what will happen that in this pore size, suppose this is a pore size, so suppose a lot of water, I will draw the diagram here. Okay, so mhm. So this is a pore size. This is a this is your all the soil media. So what will happen that water will accumulate here, and there are high chances that a smaller particle will get settled down at this place. Okay, so that this is what we call sedimentation also. So in some cases particle may settle out of the suspension and accumulate on the surface of the filter media, enhancing the filtration process. This sedimentation can help reduce the load on the filter media by removing larger particle before they reach the medium, thus prolonging its lifespan. Okay, I hope this is clear to you. So again, this is another case, that is diffusion. Diffusion means, if you have joined our first class, means diffusion happen when high concentration to, means when there is some when there is a difference in concentration. So always diffusion will happen from high concentration to low concentration. Okay, diffusion may cause particles to move randomly within this fluid, increasing the likelihood of the contact with their filter media and subsequently captured through the interception or and other mechanism. This is very simple, miss. Again, what I have discussed here in this picture. So again, what will happen that this fluid liquid containing will have high concentration of any contaminant or any suspended solid, and what will happen that that liquid will somehow diffuse on the surface of the media. Okay, so the correct option are A, B, C. So again I will be going through the question. That question was, which of the following mechanism? Just 1 minute. It is on. Which of the following are the mechanism of depth filtration? So again we have seen that interception is one process, sedimentation is also one process, and diffusion is also another process. Okay. So this was question number one. So as no one has joined, I'll be moving forward. Hmm. Which of the following statements is true for, is and are true for granular media filtration? Okay. So granular media filtration is a process used for water treatment. Granular means simple sand which we used in our construction and all these things. Okay. Oh, it doesn't matter if I pause because it is being recorded. Still, it will record. Hmm. Granular media filtration is a process used for water treatment where the water passes through a bed of granular materials such as sand, anthracite, activated carbon to remove suspended solid and impurities. Okay, so generally, with whatever remember in filtration system, whether it is rapid or slow sand, we use this kind of material only. Okay, there are some advanced material where they use activated carbon and blah blah blah, but that is costly. But for cost effective method, we generally use gravel, sand, etc. Okay, are removed. As the water flow, the filter media particles are trapped within the wide spaces through the grains of media. In granular media filtration, as the filter operate over the time, the trapped particle accumulate within the filter media. This accumulation lead to phenomena known as head loss. Okay, which is a pressure drop experienced by water as it passes through the filter. Essentially, the more particle accumulate the filter bed, the flow path for the water restrained, resulting in an increase in head loss. So, what happened that generally, I know you are aware of this head loss. Yeah, water pressure. So, generally, what will happen that when this pore size was empty, so all the water will move easily in the system. But as soon as these particles start getting accumulated here or everywhere in the particles in the media, so it will cause something called head loss. Okay, and what will happen that the rate at which water was going through the filtration mode, as the pressure has dropped from what was happening that initially all the pressure was being applied on the water, so as there was no any kind of resistance or anything, so water was easily getting passed through the filter media. So now what is happening that all the pore which is present there have been trapped with some kind of suspended particles. So this leads to head loss, and in this way what will happen that it will uh, the water which was flowing at the say x rate, so the flow rate, so it will decrease from x. So this is all due to head loss. Okay, so what is head loss and all this thing, head loss calculation will be discussed in the another question. Okay, so for now just remember this theoretical part essentially as so therefore, the correct statement is that head loss increases with the increase in time of the operation. This because the filtration operates for the longer duration, more particles are trapped media, causing the increase in resistance to the flow through the filter bed. So this was all theory related to this question. So the question was which of the following is true. So what is happening that this statement is correct, that head loss increases with increase in type of operation. Okay, this is incorrect. This is ripening generally occur. What is this ripening? Filter ripening generally occurs in 24 hour. No, this did not occur in 24 hour. What is this filter ripening? I will discuss at the end of the lecture. Okay. So there are two concepts related to this filter ripening and filter breakthrough. So I just want to discuss both things together. So that's why I'm not discussing it here. For now, you can mark the C. Okay. Mm-hmm. So consider the following statement related to the backwashing of the rapid gravity filter. Okay. The statement backwash velocity must be lower than the settling velocity of the smallest media particle. Okay. The second statement is the total volume of the media weight as well as the total volume increases during backwash. Okay. So this statement is you can without knowing anything about the filter, you can just mark this answer as this is incorrect, because suppose if you have prepared anything which has some kind of volume, now what is happening that you are back washing. So I am assuming that you are aware of this back washing. So in short what we say that when there is a breakdown of the filter, yeah, head loss is more than 3 meter. Generally it is 3 meters. So there what will happen that with time this head loss will increase. So if the head loss is 3 meter, we pass some water, so that what will happen that the particle which was suspended there will get removed, and it will be taken out, so that our media is again free from any trapped particles from the contaminated water. So this is called backwashing. So now you suppose if you have used x meter cube of water, x meter cube of sand in your filtration medium. So this backwashing will neither decrease your sand, neither increase your sand. It will, the volume will be constant. So this is a false statement. Okay, so we will discussing more about the statement one. So means either your answer will be A or D. Okay. Uh-huh. So the backwash velocity must be lower than the settling. The statement one was the backwash velocity must be lower than the settling velocity of the smallest particle. So this statement is generally true. The backwash velocity is higher than the settling velocity of the smallest. It can cause the media to loss or carry over the fine particles. So I hope you remember of this Vs is equal to under root GDGS minus 1 divided by 18 mu. Sorry, 18 CD. 18 CD? I don't know. So just let me check it one. What is this? Sorry, only 18 CD, not C. 4 by 3 GD GS minus 1 divided by CD. So this is settling velocity. Okay. Hmm. So what is happening that you are supplying some water. So what will obviously what will happen that if the velocity should be much lower, should be very low. We will be passing water at some velocity at some flow rate, and the area of the this your sand filter is fixed. Uh, Suppose this is your sand filter, so this area is fixed. Okay, so you must supply your backwashing flow. Your backwash flow should be at some constant rate, and that rate divided by this area will give velocity. So now what happened that we know that there is one smaller particle which has some kind of velocity. We know this settling velocity. So now imagine that if you have you are applying your water to you are applying backwash with very high velocity. So there are chances the smallest particle will get away from the your rapid sand filter, and it might cause loss to your filtration media, and we don't want that. So how to make sure that during backwash all the particle which is there in the filtration media remain in the filter media? So for that what we do that we make sure that the for the smallest particle, whatever the settling velocity is there, my backwash velocity should be lower than what is there, whatever velocity is there for this smallest particle. So this statement is true. And why it is done? It is done to save our filtered media. So as discussed this statement, I was saying this statement is connect doing backwashing the expand as the water flow through, but the total volume of the media and the remain constant. Okay, backwashing serves to clean the filter media by loosening and remove the trapped particle, but it does not increase the total volume of the media and or media solids. Okay, so the statement correct option is A, that is the statement 1 is correct and statement 2 is wrong. Okay, so I hope this is clear to you. So the answer of this question was A. Okay, if you have oh sorry, hmm, which of the following is not correct? So they I feel difficulty in pronunciation of this term, so they I will just calling is layer. Okay, so layer is not formed in slow sand filter. So before knowing what is this layer, you should know what how slow sand filter work and all these things. So if you have gone through the lecture, you must have gone in the detail that how this slow sand filters work and all these things. Okay, layer increases the quantity of filtration. This layer takes around 1 hour to get formed after being scraped while cleaning the filter. So how we clean our filter? Through backwash only. Okay, and this layer is formed by process of biological metabolism by microorganisms. So you have to mark not correct statement. Okay na? So this is a kind of biological layer which forms above the sand filter in slow sand filter. Okay, so this is a general picture of slow sand filter. It contains sand, gravel, and at the bottom of this media there is one collection system. Okay, so as in the first slide I was saying that for filtration, what is our main target? Our main target is to reduce the turbidity of the water. Okay, actually in filtration, actually it's not my target. When we remove any if you look at the definition of this filtration on internet, you will generally see that to remove the colloidal particles, to remove the suspended particles, and then all these things. So how will you make sure that after filtration all your suspended particles and the colloidal particles has been removed? To measure that quantity, a characteristic or a parameter that is checked for the water, that is turbidity. So before entering this sand filtration, the turbidity of the water will be around 30 to 60 NTU. Flow is NTU. This is a unit of turbidity. So after treatment, it should be less than 1 NTU. So that way we can ensure that our filtration is working very fine. Okay, so if you are not getting any water which had if you are getting water which has turbidity less greater than 1 NTU, means your filtration has there is one or there is something either it has reached maximum head loss, or there is some problem in the filtration media that your filter is not working properly. Okay, so you should always remember this theoretical concept and how to interpret that theoretical definition of filtration. Okay, so in general filter. So effluent will have a turbidity of around 30 to 60 NTU, and the effluent will have a turbidity less than 1 NTU. Okay, so what happened that it contains one biological layer. Okay, so it also act as a media. Okay, so sand is a filtration media. D, the depth of the filter media, which is around 1 meter. Sand size is generally 0.12 to 0.33 mm. Porosity is around 0.4 to 0.5. Then there is under drainage system. Okay, so support media, 3 graded layer, 2 to 8 mm, 8 to 16 to 30 mm of water, sorry, gravel is kept here. Collection system, there is a perforated pipe will be kept here, that will collect our system. Flow rate is very slow here, that is 0.1 meter cube per meter square per hour. Okay, so the water passes slowly through the sand from the top to bottom. Water will pass very slowly. You can just imagine 0.1 meter per hour. Okay, miss I am defining in the term of velocity, but generally flow rate is always defined. Generally, this is whenever we are talking in the terms of volume or any system, we always define flow filtration rate या velocity in terms of meter cube per meter square per hour. Okay, so you can just imagine 0.1 meter in 1 hour means 100 centimeter, 100 centimeter, sorry, 10 centimeter in 1 hour. This is really slow. Okay, so that's why the name slow sand filtration. Okay, the sand particles at the top of filter media are colonized by microscope organism including bacteria and protozoa. So what will happen that this sand media, we know that this sand media is a home to this many bacteria and all this thing. And water also contains some kind of will contain some kind, so all these will combine and they'll what will happen that they will form some kind of a colony. In time a slime layer which is known as this thing. I won't try to pronounce it. In a time slime layer, remember this is slime. I hope you know what is slime. You must have seen slime. Is form This layer is responsible for filtering the water. The mechanism of filtration is predominantly straining. What is this straining? When I will be discussing this, miss, you can remember straining. What miss, there is two particles, there is some pore. Okay na, and it will have some pore size, say 1 mm, 1 micrometer, and the particle size is greater than that. Suppose it is x, miss, remember this is x. Take very small unit, and it has the particle which is coming here, that has a size of 1.1 1.1x. Okay, so what will happen that it will get trapped, and it will it will create some kind of a strain. I hope what do you mean, I hope you must be familiar of this strain and stress. So this is similar. So generally, in terms of filtration, we say that if the pore size is smaller than the particle size, then it is causing a strain. Okay, so obviously, but water is coming, a pore has been trapped, so again more water will come. So obviously, this smaller particle which has trapped between these two particles will cause a kind of a strain on these two particles. Okay, so that's why it is saying that straining. But remember, these things do not happen in rapid sand filtration. I will just, when I will be discussing in rapid sand filtration, you can see there. Okay, the process that occurs in this layer are enormously complex and varied, but the principle is one of the mechanism straining of the most of the suspended particle in the thin dense layer, in which the pore may be very much less than the micron. So how this is a straining thing? So the pore size between two particles in this slime layer is very small, that is in micron, that is in 10 to the power minus 6 meter. The thickness of this layer increases with the time from the initial installation to the point where the flow rates become unacceptably small. So what happened that in this low sand the filter already the flow is very small, that is 0.1 uh, 0.1 meter per hour. Now remember that when we are analyzing our system, we make sure that the flow rate is, the water which is being collected has a uniform flow rate. Now this flow rate has all may go to up, they must have some limit, that it should not go below that flow rate. So if doing collection of water, if you are seeing that this flow rate is much less than 0.1 meter cube per meter square per day, then means that layer has grow too thick, so you have to remove that. Okay, after the initial installation, the SSF formation of this layer in the bed may take a days or weeks depending upon the strongly on the ambient temperature. So remember, it takes days or weeks to form depending upon the temperature of the system. During this period, the processed water is unsafe for human consumption. Okay, so during this formation, the whatever the water is being coming out from the filtration is very unsafe for the human consumption. That's why in what is happening that, see, this slow sand filtration is taking too much time to filter a small quantity of the water. So that's why this slow sand filtration is generally not used at higher scale. For smaller scale, this is used, but for mm, hmm, but for larger scale, this is not used. Okay. Hmm. So when the filtration rate drops unacceptably, say after 6 months, the SSF must be cleaned carefully, removing 25 mm of top layer, which includes the most of the existing layer, after dropping the water level to significantly below the latter. Okay. So for one, what happened that for slow sand filter, imagine that this much thick amount of this layer has formed, so we won't be removing complete this slime layer, we will be only removing up to some part only, because we know that this, if I remove this layer, so it will again takes months to form, and this is main mechanism involved in slow sand filter. So removing all this slime layer will just create a problem for my sand filter. So instead of removing completely, we just remove some part. So it is carefully removing about 25 ml of the 25 mm, that is 2.5 centimeter of the top layer. Okay. So in time, the depth of the original bed of the sand will reduce by cleaning process about 0.75 meter, which is, when the original depth must be restored, as a new sand will be almost. So now remember that this layer is not forming separately, this is a part of the sand only. So what will happen that during removal we will be removing that sand only. Okay, so that is, this is what is written here. In the time, the depth of the original weight of the sand will have reduced by cleaning process to about 0.75 centimeter, that is 30 inch, when the original depth must be restored, as a new sand will be almost divided the biological placing it on the top of the existing sand will require an excessive long time to develop a new layer. To accelerate this process, the layer is first removed and discarded, and then the most of the existing bed is removed and the aside for reuse. This new sand is placed in position and then covered with the original bed. In this way, biological activity and the new layer are more rapidly restored. Okay, so I hope this is very clear to you, like how this process work. We do not remove, miss, what happened that you have removed the this slime layer. So now adding and in doing so, you have also remove some sand. So now you want to replenish that sand, so you cannot replenish on the top of that sand. So what happened that we remove all the sand. This is what this is very difficult task. So what happened that whatever the layer is first removed and discarded, and the most of the existing bed is removed and set aside for reuse, and we add some new sand, and above that we add the existing layer, so that the growth can be accelerated. Okay, so the correct answer is, depending upon the discussion, you can answer this answer. The correct answer is A and C. So they, remember, they are asking not correct. Okay, the smudge is not formed in slow sand filter, but remember this is always formed in the slow sand filter. So this is my answer, because they are asking not correct. So obviously this is definitely not correct. Increases with the quality of filtration. Obviously this layer increases with the quality of filtration. So this won't be my answer. This, because this is a correct statement. This layer takes around 1 hour. No, it takes more than 1 hour. It takes weeks to form. Okay, after being escaped while cleaning the water. Okay, so obviously this is also incorrect, and this is my answer. Okay, and lastly, this is formed by the process of biological metabolism. Yes, this is correct, but this is not my answer. Okay, I hope this is clear to you. Hmm. Coming to the one numerical question, calculate the percentage of recovery of reverse osmosis. So again, remember, this reverse osmosis is an advanced kind of filtration. Okay, reverse osmosis, use of membrane. So this slow sand filtration and rapid sand filtration is very conventional method. Currently people are using reverse osmosis. Then you can, in your house also you are using filters, and you can just check which mechanism they are using. Okay, generally, sorry, you can just check it. Okay. Hmm. So they are saying that calculate the percentage recovery, the feed water flow rate. So retention flow rate and TDS in the feed water and TDS in the permeate. Okay, so remember, what is this flow rate? Feed water means, suppose this was your filter, whatever water you are adding, that is, this is known as feed water. So it will be obviously coming at some flow rate, so that is known as feed water flow rate. Okay, uh, then TDS in the feed water and the TDS in the permeate. Okay, the permeate means whatever the water we are getting after filtration. So remember, uh, reverse osmosis, how this happens. So this way, one part will contain some fresh water. So this is for fresh water, filtered water, and this is for unfiltered water. Okay, so what happened that they have also given the a hint also, that percentage recovery is permeate flow rate divided by feed flow water flow rate. Okay, so they have not given the this permeate flow rate and feed water flow rate, they have already given. Okay, So I will be calculating this permeate water flow rate. Okay, so already this thing is given in the question. This is the percentage recovery is also given in the question. So this permeate flow rate is given by, obviously this what will happen, retentate flow water. So this permeate and retentate means whatever water I am getting, whatever there will be a flow rate at this, the water will be getting retained, and I will be subtracting that. So upon that I will be getting the flow rate of the permeate. So permeate flow rate come out to be 1700 meter cube per second, and we know the feed rate is 2700. Okay, so the percentage recovery is 73.91%. These two data were just to get you confused. Okay, but only we need the data of these two things only. Okay, so the percentage recovery is 73%, 73.91%. The percentage recovery of the reverse osmosis unit is approximately 73.91 percentage. Okay. Hmm. So again, coming to the numerical question related to filtration only. So till now we have discussed 5 questions. All are related to filtration only. Coming to the sixth question. A sand filter which is provide water treatment to the population of 1.2 lakh. Remember, 1.2 lakh. Average water demand is this much. Okay, 140 liter per capita per day. Means one in a day per person is requiring around 140 liter. The rate of filtration is, rate at which water is being filtered is 16 meter cube per meter square per hour. Means 16 meter cube per hour. You can just say, but whenever you are writing, make sure to write in this manner only. Okay. If the design allow filter water storage to meet the back washing, so remember what happens generally. Generally, suppose if this is a filter system, it will filter say x amount of water. So we will always store some kind of water, some extra water, say 5% of this filter water, 5% extra of this filter water for back washing purpose. Okay, but in this case they are saying that they are not storing extra. So if you have gone through the lecture, the numerical which have been discussed in the class, in that question you can see that they have said that apart from filtering they are storing 5% extra for back washing. Okay, so but in this case they are saying that whatever the water is being filtered, that is sufficient for, they are just managing somehow some amount from that filter water for back washing purpose also. So means in our numerical where there will be a change, I will just point out. Okay, but remember this, what does this statements mean? Okay, that the storage meet the backwashing means they don't have to store some extra water. Okay, the filter wedge is required to expand 0.4 meter, the required backwash velocity and the given data. So remember what happened, that this was your sand. So this, when this water will go, there will be a rise in height of this sand weight. So that this is being expanded by 0.4 meter. So you have to calculate that thing. Okay, means you have to calculate uh, what is this backflow. So remember there are generally two three things. This velocity should be less than your smallest particle size settling velocity. Then it should be a function of this expansion. So there has been some empirical formula given, so we will be directly using that formula for calculation of this backwashing. So the what are the given data? Porosity of the unexpanded bed, remember, porosity of unexpanded bed, then coefficient of drag, then kinematic viscosity. Means from this data you can have an idea that they are asking you to calculate the settling velocity. Filter media, mean diameter is also given, the specific gravity is also given, the density is also, everything is given to you. So just you have to use, see these data is for note this thing. But apart from this, 8 1 2 3 4 5 5 things are being given. It is just giving you indication that you have to calculate settling velocity. So how this depth of the media and this porosity will be used, I will be discussing later. Okay. So what happened that this backwashing is given by Richardson-Jackie equation. Okay, where they said that they say that the porosity of this expanded bed. Okay, remember this e this a small e means somewhere you must have seen written neta also. Okay, but here I am using this epsilon symbol because this is what is being used in your class notes also. So for the expansion weight is given by backwashing velocity divided by settling velocity to the power 0.22471 into Reynolds number to power zero point 0.1 Reynolds number of expanded weight, but the expanded weight, Reynolds number for expanded, sorry, no, this is just RE is just indication for Reynolds number. Okay, and VV is backwashing velocity and VS is VV is backwashing velocity and Vs is settling velocity. Okay, that is 4 by 3 into Gd into Gs minus 1 divided by Cd. Okay. Hmm. By just checking whether this formula is correct. Okay. So given depending on the given data, I will be calculating this backwashing velocity Vs, that is under root 4 by 3 9.81 me, uh, meter per second square into 0.6, because this mean diameter is 0.6 mm. 0.6 into 10 to the power minus 3 into gs they have given 2.5 minus 1 and cd they have given 5.02. So from that vs will be 0.04. You can check it, this meter and meter will combine, it will form meter square. These all are unitless quantity, and this second square will again come out to, and it will form second. So 0.048 meter per second. Okay. So depending upon the, and we also know the formula of Reynolds number. So re is equal to vs velocity, settling velocity, into dimension divided by kinematic viscosity. All data has been given to you. From that you can say find out this Reynolds number has come out to be 28.68. This is a unitless quantity. Okay, you can just, you can see here meter square will get cancelled out, second will get cancelled out. Okay, so 28.68 is the Reynolds number. So the second question is how to find this expanded weight, porosity of the this expanded weight. Okay, so a means if you have gone through the lecture, there has been some derivation related to that, like how can you measure it. So I am just writing you direct formula, and the concept which is involved in hmm, the concept which is involved in the to find the porosity of expanded bed is given here. The volume of the solid is same in expanded bed as well as unexpanded bed. Obviously this I have discussed in the second or third question only, that the volume of the solid means volume of the sand medium is same, that is for expanded bed and an expanded weight. So depending upon this, if you do some math, how this math is done, you can just go and check the video lecture. You will be coming to this derivation. You will be coming to this equation, that 1 minus expanded porosity into depth of the expanded bed is equal to 1 minus E into 1 minus unex, unexpanded porosity into this depth of the bed. So D is already given you 1 meter, and in question it is written that after expansion there is expansion of 0.4 meter. So D will be 1.4 meter and E is already given as 0.5. So I will be putting all the value here, and after putting the value you can see that expanded porosity comes out to be 0.64. So this can be expected also. So during expansion the porosity of the distance between the two particles will increase, creating a uh, mm, creating a high porous medium. Okay, so that's why porosity has increased. Okay, so I will be substituting all the value here, and after calculation I will be getting the back passing velocity as 0.042 meter per second. Okay, so if we imagine that this is my smallest particle, so we have made sure they have just given a mean diameter of the particle. So there might be some particle which is a dimension less than 0.6 mm. So the settling velocity of that particle will be larger than this particle. Okay, if it is not that case, then there are chances that particle may get lost during backwashing. So this kind of calculation is being done for design of any filtration medium. Okay, so I hope this is clear to you. Just 1 minute. Hmm. I hope this is clear to you. So coming to the based on the data, given data, head loss in the filter before backwashing. So what happened that generally when the head loss, obviously there is some apparatus attached to this rapid sand filter back that always measure the back pressure. Okay, so you can see the just I will just for your purpose, no, I won't do that. But you can always go miss check on miss your study material. There they have just shown miss there will be one number 1 2 3 visual to be closed, visual to be open. You can refer to any standard book also. From there you can see that, and at the end of filter media there is one pressure that will keep measuring the head loss. Once that head loss has crossed 3 meter, they will just miss that filter required miss they will be measuring other thing also, but it is convenient that whenever your head loss is 3 meter, it is there is high chances means there is a 100% guarantee that the water which is coming from the filter is not filtered, or it very high it has high turbidity. Means that filter media require require backwashing. Okay, so this depending upon the density of the solid and all this thing, the head loss is generally given by this equation. Okay, so you can and there is one another formula that I will be discussing later at the end of the discussion. But for now, and derivation of this is already given in your lecture. So if you put out this value, it is saying 0.75 meter. So this is also okay, means they have designed their filtration in system in such a way that 0.7 mm is minimum for backwashing. But for bigger plant, generally it goes to 3 mm or 3 meter also. Okay, okay. No, I hope this is clear to you. Coming to the next question. Just 1 minute. Actually, in my area today is holy. Hmm. The question is, a water treatment plant. Sorry for the inconvenience. A water treatment plant in a town is proposed to be expanded. So, with the increasing, we know that with the time, with the population increase, water demand also increases. So, what are they planning that they are planning to expand their water treatment plant, because the net design flow rate is 1 meter cube per second. The deep bed granular soil filter with the design of loading rate of this material is to be used. Okay, so based on some calculation, they have come out to be in if the area of the each filter box is limited to 5 meter square of the surface, 50 meter square of surface area, how many filter boxes are required? Answer to the nearest digit. Okay, So this is a very simple question based on this unit match and all this thing. So you can do it, miss, anyone can do it. So this design flow rate is given. Okay, so you can the total volume, how much volume is design flow rate, is 1 meter cube per second, means 1 meter 86 86,400 meter cube per day. And the total surface area, so we know that this is the flow rate and this is the loading rate. So from the loading total volume and the design loading rate, we can find out the total surface area required for the filtration. Okay, so this is, remember, most of the question which is related to this water treatment unit is just based on match, unit match. If you don't know theory, this is not good, this is not a good thing that you don't know the theory. But if you are facing some problem, if you know the basic things, you can calculate the answer, or you can find out the answer just matching the unit. But you should know that which unit should be matched. Okay, so I'm not recommending, but I'm just saying this for in a point of, in a competitive exam, in a point of view of a competitive exam. But if you are appearing for any theoretical exam, you must be aware on this thing that you have to write in a this way. Okay, so this is total volume, this is the design flow rate, design loading rate is 600 meter cube per day per meter square. This meter cube, this meter cube, this day, this day will get cancelled out and I will be getting 144 meter square. Okay, and they already say that surface area of the air filter box is 50 meter square, so it will give out to be 2.888, and they are asking to the nearest integer which is equal to 3. Okay, so this was very simple question. So there are chances that initially only one or two only one or two only one or two filtration unit is there as the water demand has increased. So there is need to increase in the uh, uh, there is a need to increase in the filtration box. Okay, so that's why the number of box should be 3. So the last question of this day. After that I will be discussing some theoretical part. If one of the filter box is out of service, the new loading rate will exceed the design loading rate. So this is true or false. So if one of the service is out, so it will be 2. So the area of the two filter box will be 100 meter square, and we know that the loading rate is this much, and area is this, so it is 864 meter cube day per meter square, which is higher than the design loading rate, that is 600. Hmm. So obviously our design loading rate is only 600, means our whatever the unit was there, it was only designed to design at a loading rate of 600. What was the unit of 6? What was the unit was? Generally, I should have written the meter cube per day per meter square. Okay. So obviously this is increasing this design loading rate. So obviously it will cause a problem. Okay. So if this statement is true, and this, if you look at the design in point of design view, this is not okay. Okay, so till now I have covered all the theory part. So what I will be doing, I will be discussing some concept related to rapids and filtration. Okay, so this rapid and this slows only differ by this one thing, that is flow rate. In slow sand filter, the flow is slow, but in rapids and filter, the flow rate is very high. Okay, we will see here. So water containing distillate particle turbidity. distilled particle turbidity 5 to 10 is applied to the sand bed. Okay, almost all particles in the effluent are retained in the sand bed such that the water effluent has the turbidity less than. My target was to remove water having turbidity very less turbid. Okay, this is the main concept of filtration. Whatever be definition, if you refer 10 book, you will get 10 kind of definition. But the overall gist of all those books will be that you have to reduce turbidity. Okay, so this will your media. It will contain it will contain this a layer of sand, water containing about around this kind of. Remember, in for case of slow sand filter, we were applying 30 NTU. Okay, because we know that the time will it will require very high time. So somehow the mechanism in such a way that it can remove from 30 to 1 NTU. But what is happening in rapid sand filtration? This time very the retention time is very less. Okay, so how much retention time is there? Just let me see. Retention time is around 2 to 3 days. Okay, na. Hmm. Sometimes for some cases it is even less also. But for the rapid sand filter, you can see it was in months. Okay, so what is happening, that's why retention time is less. So we are before introducing my water sample to this rapid sand filtration unit, we are making sure that the turbidity of the water which is going in the this filtration unit is much less than what was being given to the sand filtration. Okay, so there will be a gravel after this filtration, and then this is collection system. Okay, and then finally we will be getting effluent having a turbidity 1 NTU. This is diameter, this is. So remember, this is the this was I was saying, this is how there will be two water is uh, poured here, and a pressure will be measured. Whatever the difference is there initially, what will happen that this level will be, you can imagine. So the head loss will be measured with the help of these two pressure gauge which is installed in the rapid sand filtration. Okay, flow through the water results in the head loss. Okay, magnitude of head loss increases as more and more particles are retained in the sand bed. Hence, the sand bed must be cleaned properly to ensure water flow at the required rate. Okay, this already I have discussed. So this is the schematic representation how flow happens through the media. So generally, there are several media. So water will be coming from anywhere, and we will be going through this. This is just represent flow of the water. It doesn't contain. Sorry, it does not contain any kind of particles. So now happen, obviously this water will also the water which is coming contain some colloidal particle or suspended particle. So what will happen that these particles will get attached. You can see that either it is getting but you can see that the water is either attaching itself, means absorbing itself, or but nowhere you can see that any particle is between two particles, between the pores of two particles. Okay, means this is just representing the one concept which I was discussing, that is straining. So in this case you can interfere, you can say one thing, the whatever the pore size is there is much larger than the particle size of this material. Okay, that's why you can see that some particle is here also, some particle has come here also, and it has some kind of has settled down here. It has get trapped or absorbed. Here miss at some, at every place something is happening. Here you can see that it has just simply settled down. Here you can see that it has get adsorbed. Here also it has get adsorbed. Okay, here you can see the surface area is very large, so that's why it has get settled down. This is a best picture of getting settlement. The area is providing for settlement only. Okay, but in at no location the two particles are trapped between two medium. The only only way to make sure that two particles are not getting attached between two media is that to make sure that the pore size of this medium is very large as compared to the pore particle size which is being so remember, so this rapid sand filtration is also considered as a costly method because before passing your water through this rapid sand filtration you have to make sure that your particle has a water has a turbidity around 5 to 10. If miss how you have miss in sand filter you were using 30 NTU, but here you are using just 10 NTU. Miss with the some mechanism or with some unit you have made sure that whatever the turbidity was being caused by other particle or other colloidal particle are being removed from the system. Okay, so that's why you are making sure, that's why miss before passing your water through the rapid sand filtration you have to pre-treat it. Okay, I hope this is clear to you. Hmm. So again there is a question which I was discussing. So first before that you should know that what is this straining. So you can see that between two particles between two particles this is getting trapped, this is getting trapped, so it is causing some kind of a strain in the medium. So now imagine, but in this picture you can see that at no such location you can find such things. We have I have made sure from the class notes, I have taken it from my class notes. So it was made in such a way that it has been made sure that no such schematics is being shown here, so that by seeing this picture one can interfere that simple sedimentation, diffusion, absorption is happening but no straining is happening. Okay, the question is why. The question is again same thing, what I have told you that what I have told you, I have told you that pore size should be larger than that, the porosity should be larger than the particle size. So that this is what is I have written here. The filtration media is a sand of size of 0.5 mm. Okay, the porosity is around this much, which means nearly half of the sand bed is empty. Okay, thus the pore size Thus, the pore size is similar to the sand grain. For particle to be removed by straining, the size should be similar to the pore size. However, the particle applied to the filter are more than an order of lower than the 10 micron. Okay, so you can see that this is much lower than these two size. So water will easily pass. Okay, hence the mechanisms of the particle removal in the RSF cannot be straining. So I hope this is clear to you. No one is here, so no one will reject me. But this is what is, so this is what uh, the concept of a staining looks like in simple way. Rapid sand filter. So you can remember that when obviously when the particle size is large the turbidity is more. So the water which is being feed here we see the particles applied to the filters, means we are applying different kind of water in slow sand filter and we are applying different kind of water in rapid sand filter. Okay, so here head loss can be, one can measure the head loss directly by seeing the instrument, or it also depends some empirical formula has also developed, such as Kármán Cauchy equation. Okay, so this is given by this equation. I think one should remember this equation because this is in 2021. Actually, frequently this question is being asked in GATE examination. So the person who prepare the question of GATE expect from you that you should know this formula. Sometime I don't know, in 2021 it was not written in the, but they have given this question. Okay, this Kármán Cauchy equation. Okay, so this thing I have already, so you can see that for sand medium, many see many books or many book generally say that the sand which is used in such slow sand filter is very of a small size. In rapid sand filter is of large. There is no such thing. Okay, generally sand which is used here and there also are of same size. So here sand size is around 0.5 mm. Okay, and just let me check what kind of sand was used in slow sand filter. Oh nice, sorry, I said something wrong. In sand filter it is generally a smaller particles. Okay now, sorry, I take my words back. In sand, in porosity is almost same in the for both cases, but this particles sand size is much smaller in slow sand filter. Sorry, I mean, I just I must have misread something. Okay. Hmm. So let me clear this. Hmm. This depth of the filter, the particle size is 0.5 mm, which is much larger than the rapid sand filtration. Gravel again, this is same as compared to that system. So slow sand filter. And head loss, which is the filtration rate is, see here filtration rate is 8 meter cube per meter square per hour, means 12 meter cube, 12 meter per hour water means 12 meter cube of water per area is being filtered out. So you can imagine how much water is being filtered in 1 hour depending on the surface area. And you can see the box filter. You also remember the, you can imagine it was around 50 meter square. So depending upon that you can just imagine how much water is filtered at in 1 hour. Okay, so coming to again to this equation, the head loss is given by F by phi. F is a empirical formula which depend upon this Reynolds number. uh, this depend upon the Reynolds number and the NR, that is obviously phi d Vs divided by mu, and this phi is the safe factor, and generally our gravels is a sphere only, so that's why we take 1 F 1 minus alpha dy v. This is d, and this is the depth of the sand, and d is the diameter of your sand particle settling velocity, and this g is the 9.8 meters. So for I have calculated for this thing, 0 0.6 thing only. uh, for it d is equal to 0 0.6, the particle size is 5 mm. So you can, for 5 mm you can the settling velocity, oh sorry, uh, filter it's just a numerical, just don't I don't remember its exact wording, but they have said that this settling velocity is this much and diameter of this particle is this thing. We can calculate the NR. Alpha is 0.45. I have assumed alpha is 0. Generally 45. Then I can calculate this F, and I can substitute the value here. And after substituting for the value, uh, after substituting the value, HC will come out to be 0.0347. 0.347. Okay, head loss. So at different point, hmm, so means initially this will be your head loss. Okay, depending on hmm, hmm. So again I was saying about two concept, sorry, I was saying about these two three things, that is filter ripening and particle breakthrough. So what happened that as soon as I add some water, it does not happen that our water will be coming out to be filtered. Initially the filter system takes some time to get adjust to the condition or the water which I am adding. So that is known as filter ripening. And after some time, what will happen that due to accumulation of more and more particles, this filter, there will be a particle breakdown, and our filter will finally get break. Our filter will finally break down, and it will consider a particle breakthrough. There is a question that evolution of effluent turbidity during filter run is shown in the water. So initially you have added water 5 to 10 NTU. So after when you collected, initially it should be less than 1, but initially it is not less than 1. It is greater than 1, but after some time your turbidity is less than 1. And what happened that after after several hours, after several days, your whatever the original water which you were adding was coming out. So you have to explain why the first question is why the filter has a turbidity greater than 1 NTU. Okay. Explain why the effluent turbidity is slightly elevated at the start of the filter run, and then to fall below 1 NTU. And the second thing is explain how toward the end of the filter run the particle breakthrough occur and turbidity increases to greater than 1 NTU. Okay. So the first concept is related to filter ripening, and the second concept is related to filter breakthrough. Okay. So I will be discussing one by one. So what is this filter ripening? The destabilized particle applied to the filter media are retained by the collector in the filter sand. Remember, destabilized particle. Again, I am referring this as destabilized means. Again, I am referring to this what do we, coagulation or flocculation. In coagulation, the particle were stable. That's why they were not settling. We added some chemical, we destabilize it, and it gets settled down. So that they are talking about that destabilized particles are retained by the collector in the filter sand. So obviously, this was your filter media. So it will be collected by those particles will be collected by this filter media. However, some particles do manage to evacuate. So if you have gone through this picture, so you can see that some particle, this particle, this particle has gone through this filter media. Okay. uh, at the start of the filter, the number of particles escaping are relatively large, hence the effluent turbidity from the water is more than 1 NTU. That's why what is the water sample which is collecting at the bottom of the tank obviously contain those particles also. That's why the turbidity is high. Okay. However, the particle collected after the filter during the initial period act as secondary collectors, increasing the total number of collectors in the filter bed. Hence, after some time, the particle retaining capacity of the filter increases and the effluent turbidity from the filter falls below NT2. This phenomenon is known as filter ripening. So I hope so. What is happening there? Initially, all pore were very clear, nothing was getting trapped, but after some time, it was just getting a start. Means it was just getting, and the filter was adjusting itself to the water which is being added in the system. So what happened that initially due to this, some particle were getting coming out directly in the water, but after some time it was getting trapped. So that's why initially turbidity was high because those particles were coming along with the water, but after some time it was smooth. Okay. Particle breakthrough due to the reduction in porosity of the due to reduction in the porosity of the filter bed, due to reduction in the porosity of the filter bed during the filter run, the pore velocity in the filter media increases. Okay. Pore velocity. Now remember that whatever see, uh, uh, there was these two particles, and some particles say suppose get trapped here, some particle gets trapped here with time. So what is happening that this pore size has now decreased, or you can say that the area by which the water was flowing has decreased. And we know that for q is given by v is given by q by a. And now whatever the flow rate of water is being maintained from the top of the, we are already maintaining a constant flow rate. Okay. So now the area has decreased, so eventually the velocity will, sorry, area has decreased, so eventually velocity will decrease. Okay. Sorry, area has decreased, so velocity will increase. Okay. So this is what is happening due to reduction of the pore velocity in the filter media increases. Thus the particle already collected in the filter media are getting greater shear force as water pushes them. So now happen the water coming here has high velocity, and there is some particles which is attached here. Okay. So what will happen, that water will be coming at high velocity, will strike it directly. So it will experience some kind of a shear force. Okay, so because it is applying some kind of force on the small particle. Some of the collected particles become dislodged due to this and get suspended in the water again. So now, as this is getting some kind of shear force, so what will happen, that this will experience some kind of force, and it will again detach from the from the social media, and social media, I'm saying filter media, and it will again suspended in the system, and that will eventually come out of the water. And now imagine it is happening at one location, and your filter has a area of around 50 meter square. So at many places this is happening, so overall the water which will coming will have a turbidity larger than 1 NTU. Okay, then particle are again collected below. In this fashion, particle penetration deeper into the filtration progress during the filter run. Particle penetration ultimately reaches the bottom of the layer. Once dislodged from this layer, the particle came out the filter along with the effluent. This phenomena is known as breakthrough. Okay, so this is known as breakthrough. I hope this is clear to you. Okay, so that's why you can say, this is very straightforward, nothing science involved in this, but these are some of the general concepts which you should know. Okay, at last I just don't before after that, what is alkalinity. So some of the things which was left most important is the backwashing. A filter has to be stopped every few hours due to excessive head loss guilt. After stopping the filter is drained. Then the filter water stored in the backwash tank is passed to the filtered in an upflow mode. Upflow mode means generally what was happening. This was your thing. Water was coming here, and this was your sand media. It was getting filtered, but in backwash water will come from here, and this will expand, and this is known as backwashing. Okay, the backwash rate is generally 1 meter cube per meter square per minute. Backwash time is not more than 5 minutes. It can be more than 5 minutes depending upon the situation, or depending on the type of filter. Okay, the backwash rate is such that the sand particle is fluidized during backwashing, means it turns into it, it do not completely get removed from the system. And how to make sure that no single particle are being get removed from the from the filter is to make sure that the backwash flow rate should be less than the settling velocity of the smallest particles. Shear force during fluidization causes the particle attached to the sand during filtration to be detached and removed with the backwash water. Sand water is thus cleaned. Okay, so what will happen, that whatever is attached here due to backwash, it will get detached, and this backwash will be again collected outside of the system, and you will be getting your sand will get cleaned. Okay, flow rate filter down time due to backwashing 30 minutes per cycle. This is a kind of design thing, ignore it. Okay, the backwasher is conveyed to the end of the head of the flocculation tank. So what happened, that this water will be again to taken to the flocculation tank, where the suspended particles which was whatever was trapped here will get collected in the form of sludge, and the water will again transferred for further treatment unit. So in this way we are making sure that no way backwash water is also being wasted. Okay, so it will again mixed with this backwash water will mix with the water which is coming for the treatment. Okay, okay, so I hope this is all clear about your again this is I hope this is clear. Discard. This is clear. This is clear to you regarding this. What do you called? What do I call? Filtration. Okay. So these three topics are covered. So I'm not going to discuss about this infection. Just let me check on which session this infection was being covered. Okay. I think it was in big six. Just let me check. Huh. So you can go to big six and you can watch that disinfection discussion question related to disinfection. But so I'm not discussing here. So about hardness. So hardness, some of the portion has been discussed here, and some of the portion will be discussed in the big nine. Okay. So big nine contains some of the numerical question related to carbonate and all these things that I will be discussing in the next week. But for now, I am discussing two concepts, that is of this thing filtration, not alkalinity and hardness. So no, before understanding what is hardness, one should have an idea of alkalinity also, because both are related thing. Okay. So miss, generally whenever the question are being framed in a any exam or anywhere, the question related to question is always framed in such a way that they will always ask you to find the hardness. They will always they will always ask you to this thing, what do I call, uh, sorry, they will always ask you to solve alkalinity question and then hardness question. Okay. So everyone is so actually I have already taught, means this is a kind of recap. Okay, many of you present here have already idea of this alkalinity. Okay. So I will give there is some alkalinity question, and then one question related to alkalinity and hardness, and that is the end of the lecture. Okay. So how do we alkalinity, how one can define alkalinity? Alkalinity is the ability of certain species to neutralize H plus ions in the water. H plus will be superscript. Okay. Hmm. Ability of certain species to neutralize H plus ions in the water. So generally due to OH minus, OH minus, that is caustic alkalinity, carbonate alkalinity, bicarbonate alkalinity. But if your water, generally wastewater does not contain phosphate, but suppose if you are sometimes it contains, sometimes it does not contain. But suppose if contain phosphate also, then all form of phosphate, that is H3 PO4 3 minus, HPO4 HPO4 2 minus, H2 PO4 minus, all these three things also cause alkalinity. Okay, because all these thing have also capacity to neutralize H plus. Okay. Neutralize, so all these things can cause alkalinity in the system. Okay. Okay, alkalinity is generally presented in milligram per liter as CaCO3. There are two method, one by experimental and one by theoretical. Experimentally, how it is defined, how it is determined. Alkalinity is determined by titrating the sample either with 0.01 normal HCl or 0.02 normal H2SO4. Indicator used are phenolphthalein and methyl orange. Okay. So what will happen, that phenolphthalein indicator, a pink phenolphthalein indicator is pink above pH 8.5 and colorless below 8.5, and similarly methyl orange is yellow above 4.5 4.3 and orange below 4.3. Okay. So and the direct form, sorry, I have not written the formula here. So what happened, that you will take sample, so what will happen, that you will take sample and you will add, first you will add phenolphthalein indicator. Okay. So what will happen that it will either turn pink or colorless depending on the pH of the system. So now imagine if it has turned pink. So what you will do that you will start titrating with the help of, sorry, you will start titrating with the help of this HCl. Generally HCl is used. Okay, so you will start titrating with this HCl. You will start titrating with HCl. So after some time what will happen that this will turn into colorless. Okay, so as soon as this turn into colorless, you will just note down the how much volume has been consumed. Say suppose x ml of HCl has been consumed from coming down to from bringing to pink to colorless. So that point is known as phenolphthalein endpoint or phenolphthalein alkalinity. Okay, this XML. Now what you will do that you will add this thing HCl, sorry, this methyl orange indicator. Obviously pH is above 8.5, so it will remain yellow, it will convert into yellow. Okay, so from colorless to yellow. Now again you will start adding HCl, and after some time what will happen that after consuming by ml, your yellow will convert into orange. Okay, so what will happen that x plus by means, so now what will happen that I will be using the concept of this normality. We know that this n1 v1 is equal to n1 v1 is equal to n2 v2. Okay, so up to this x point we have to find what is the normality at up to x. So this will be x, sorry, I have to find N1, the volume consumed by XML, N2 was 0.01 normal, and V2 suppose you have taken 10 ml of samples. Okay, so from here you can find this N1. Okay, N1, say suppose this I am calling this as P, or I am calling this as A, capital A. Okay, for similarly for what will happening that for consumption of by ml of HCl, again I have to find B into by ml is equal to what is n2. N2 is 0.02, 0.01, and this V2 is 10 ml. So again from here I will be calculating B. So what will be my total alkalinity? Total alkalinity will be summation of A plus B, whatever will be the normality. And generally what happen that whatever is the normality we multiply to convert. We always convert our answer in milligram per liter. So you can convert normality by multiplying its equivalent weight. So equivalent weight is 50 gram per liter. So for converting into milligram, I will multiplying it by 50,000. 50,000. So it will be 50,000 into A plus B. Okay. So that will be giving my total alkalinity. Okay. That will be giving my total alkalinity. Okay. Similarly, there is direct formula. Suppose you have measure pH of the system. If you measure pH of the system, you can know the OH of the system. You can measure with some instrument. You can measure carbonate and bicarbonate, and from there you can directly put the value here, and you can find the total alkalinity. Remember, this is minus H plus OH minus carbonate bicarbonate plus twice the carbonate. Remember, twice the carbonate because it has to do something with the charge and all this thing. Okay, because this is contributing twice, it has two charges. So I have explained, just remember to whatever the charge is there, it will be multiplied. When you are writing for phosphate, suppose in your phosphate is also in your system, so you will be writing plus 3 PO4. Okay, PO4, similarly 2 H2 HPO4, and 1 is 1, that is H2CO H2PO4 2 minus. Okay, or more direct formula which is generally used in your examination, that is GATE examination, is given by this milli. Generally in your question, milligram of OH minus will be given to you. You will convert milligram by dividing into, this is equal to finding this normality. Then you will be multiplying it with the equivalent of CO3. Similarly for this bicarbonate, and similarly for this carbonate, and you will be reporting your answer. Similarly, if phosphate and other ions are there, you can write here and you can report your answer. Okay. Another thing is hardness. Okay. Hmm. Sorry. Hmm. Hardness, the presence of multivalent cations present in the system, most notably calcium and magnesium. But remember, it can be due to aluminum 3 also. Just remember multivalent cation. Whatever multivalent cation is there, it will cause hardness. Sodium, calcium, sorry, not sodium, sorry, not sodium. Calcium, magnesium, aluminum, iron 2 plus, iron 3 plus, blah blah blah. Okay, if it is present in there, it will call strontium. Generally, these are present in the system, so it causes hardness. Okay, type of hardness is carbonate hardness or temporary hardness, non-carbonate hardness or permanent hardness. A question might arise that we are talking about multivalent cations, but we are defining in the form of carbonate and non-carbonate. So it is defined in this sense: if this carbonate calcium is this if this multivalent cations is attached to carbonate, means if that cations is present in the system, it will be coming from somewhere now. So if it is coming in the form of from carbonate, then it will be known as carbonate hardness. So you will be saying that this calcium is giving carbonate hardness because it is coming from this carbonate, calcium carbonate. But suppose that iron which is present in the system is not coming from this, is not attached to carbonate, then that is known as non-carbonate hardness. So this is known as the temporary hardness. Temporary hardness, it is because it can be easily removed just simply by boiling and all this thing. But non-carbonate hardness is a permanent hardness which cannot be removed by simply boiling. You need some advanced material, such as advanced material, only advanced mechanism to remove it, such as ion exchange and all this thing. Okay. Experimentally, how it is defined, how it is determined by titrating sample with EDTA in presence of EBT indicator. Okay. So what will happen that initially this EBT present in the system will form a complex with multivalent cation present in the system, and it will form red color. So initially whatever your sample is there, it will be initially EBT has a blue color. So as soon as it will as soon as you in your sample will be initially colorless. So as soon as you add EBT, it will turn into this thing red, because due to presence of calcium and magnesium or multivalent cation. So now what will happen that this you have started to add EDTA. So this EDTA has more tendency to form complex with these metal ions. So whatever this metal is present here, it will be M, not C. So whatever the metal which was initially metal valent which was forming bond with this EBT will now start forming complex with EDTA, and your solution will turn into blue, which is the original color of EBT. So that will be giving the end color or end point of your titration. The titration end point is indicated when the multivalent cations from the form complexes with the EDTA, causing the EBT to revert its original blue color. Okay. So I hope this is clear to you. Again, same concept, but here when we are applying this when we means here there is no way to express your answer in form of like we used to do this n1 v1 n2 v2, because here there we were just simply multiplying the normality of HCl and all this thing. But here for EDTA it seems very difficult. So what we do that we prepare a calibration curve. So we prepared some standard what do we call a standard hardness solution, says 0, 10, 10, 50, 50, 100, 100, 200, and on x sorry, huh, and on it will be 200. Okay. And on x-axis what? it is not erasing. Okay, let's remember. And on x-axis we will be plotting volume of EDTA consumed. Okay, EDTA consumed. Okay, so we will be plotting this. It will be a straight line, and for a known sample, we will be measuring how much EDTA has been consumed. Suppose say XML, and according to X, I will be finding my hardness. Okay, so it will be 1050 milligram per liter as CaCO3. Okay, so direct formula again, direct formula, whatever the multivalent and ion present in your system, you have to add it, and you can find this total hardness. Okay, so now the relationship is that what is the carbonate hardness, because hardness can be of due to all these things na, that is alkalinity also, sorry, carbonate also and non-carbonate also. Okay, so now imagine, and we know that alkalinity is only due to carbonate present in the system. Phosphate might be present but it is very less. Okay, but alkalinity will be almost due to hardness, and the total hardness will be summation of carbonate and non-carbonate. So we define carbonate is as minimum of these two, that is total alkalinity, total hardness or alkalinity. Now suppose imagine your total hardness is 100, and that is due to we are assuming that it can be carbonate plus non-carbonate, but alkalinity is only 50, and we know that alkalinity is only due to carbonate only. So obviously the minimum of these two will be giving my alkalinity. Okay, so the non-carbonate hardness will be total hardness minus carbonate hardness. Okay, I hope this is clear to you. A very simple question: is there a water sample environment analysis to determine its ion composition, yielding the following results? The pH is this much, TDS is this much, calcium is this much, chloride is this much, magnesium is this much, carbonate is this much, and all these things is this much. Calculate the alkalinity, total hardness, carbonate hardness, and non-carbonate hardness in milligram per liter CaCO3. Additionally, assess whether the water is suitable for drinking or not. Okay, so for this person, for this portion you can use the formula which I have given you, and for this answering the last question you have to check with the IS code. Okay. So the first thing you have to find that alkalinity will be only due to this and this, and your hardness will be only due to this and this. Okay, so first thing you have to remember, this is kind of gate question. This kind of question is being asked in gate. You can check previous year gate question, and not only gate in miss in normal exam of IIT Kanpur also, for environmental student these question are being asked. Okay, okay. So the alkalinity will be summation of this thing, milligram of OH minus divided by equivalent weight of OH minus into equivalent weight of CaCO3 into for other system also. Okay, the equivalent of CaCO3 is 100 by 2, that is 50 gram. Okay, and the equivalent of CaCO3 carbonate is 60 by 2, that is 30 gram, and equivalent weight of carbon bicarbonate is 61 by 1. Similarly for this OH minus will be 17, 16 plus 1, that is 17. Okay, so the alkalinity, so remember, as the PSC, the concentration of other ions present is around 15 milligram per liter, 183 milligram per liter. Okay, so the POH is equal to 6.1. The concentration of OH is 10 to the power minus 6.1, which is very high. So the concentration of OH minus can be neglected as compared to other two ions, which is causing alkalinity. Okay, these three are causing alkalinity. Okay, so it will be 0 plus 183 divided by 61 into 50 plus 150 divided 30 into 50, so it is 175 milligram per liter as CaCO3. Okay, why I have not multiplied by 50, it is 50 gram, because everywhere it is in milligram and this equivalent weight unit is same. Okay, now 50 gram 50 gram, so that's why I am not multiply. But if you have paid attention whenever discussing about the I have multiplied it by 50,000 because I wanted to convert gram into milligram. But here already unit is matching, so that's why I'm not converting gram into milligram. Okay. Okay, so alkalinity come out to be 175 milligram per liter. Okay, the total hardness is again due to only this calcium and magnesium, but here aluminum is also present. Okay na, so equivalent of calcium is this thing, aluminum is this thing, magnesium is this thing. So I can calculate it and it come out to be 2 to 26 milligram per liter as CaCO3. So carbonate hardness, we know that total alkalinity, total hardness, minimum of alkalinity and total hardness, and the total hardness. So again we know that alkalinity will be due to carbonate only. So carbonate hardness will be given as 175 milligram per liter, and non-carbonate hardness will be given by 226 minus 175, that is 51 milligram per liter as CaCO3. So to check whether water is suitable for drinking or not, we have to check this thing. Okay, so generally this is the code discard. This uh, so you can from here see it has all the permissible limit and requirable limit. So I will be just checking that what is the permissible total hardness should be, permissible limit is 600, total alkalinity is 600. So is my it is below 600? Yes. Obviously my alkalinity, this alkalinity, total alkalinity is 226, below 500, so it's good. It is 175, it is also good. I will be checking for other thing also, that is pH. pH is it should be 6.5 to 8.5, so that is okay. Second thing is TDS. TDS is total dissolved solid. Its permissible limit is 2000, but again it is within permissible limit. Then comes calcium chloride, calcium and chloride. Calcium, how much calcium should be there? Calcium. Hmm. Calcium should be 200 milligram per liter. Again, it is within permissible limit. Again, chloride it should be 1000. Again, it is within the permissible limit. Then comes magnesium. Is there magnesium? It should be 100. Again, it is within the permissible limit. Then come aluminum. Where is aluminum? It will be aluminum. Permissible limit is 0.2 milligram per liter. So again, so based on the calculation, I can say that my water is suitable for drinking purpose. Okay. Hmm. So based on this discussion, I can say that my water is mm, suitable for drinking purpose. Okay. So all these for was for week 9. So in the next week we will meet, and I will be discussing about this, what to call, week 10, where I will be discussing more about hardness and all. Okay, so 5 minutes left, no one is here, so I will just stop sharing and end this meeting. You are presenting, stop sharing.